Alright, so in this video I'm gonna be explaining another important article with the title Self-Repellent Random Walks and General Graphs. Achieving minimal sampling variance via nonlinear Markov chains. This HK paper in 2024. We consider random walks on discrete state spaces, such as general undirected graphs, where the random walkers are designed to approximate the target quantity over the network topology via sampling and neighborhood exploration in the form of Markov chain Monte Carlo procedures. Given any Markov chain corresponding to target probability distribution, we design a self-repellent random walk which is less likely to transition to nodes that were highly visited in the past and more likely to transition to seldom visited nodes. For a class of SRRWs parameterized by a positive real alpha, we proved that the empirical distribution of the process converges almost surely to the target distribution of the underlying Markov chain kernel. We then provide a central limit theorem and derive the exact form of the arising asymptotic covariance matrix, which allows us to show that SRRW with stronger repellence always achieves a smaller asymptotic covariance in the sense of Loevner ordering of covariance matrices, especially for SRRW-driven MCMC algorithms. We show that the decrease in asymptotic sampling variance is of order of 1 over alpha, eventually going down to 0. After generalizing these results for a class of weighted empirical measures, we use them as a stepping stone to show that a similar performance ordering can also be obtained for distributed stochastic optimization tasks using token algorithms. Random walk techniques are a staple in statistics and learning. Markov chains such as Metropolis, Hastings, random walk, designed to achieve any given target probability distribution as its stationary measure, are widely used as MCMC samplers. The local nature of information required to compute state transition probabilities means that the algorithms scale well and are robustly implementable over state spaces such as large graphs or networks with general topologies. However, classic Markov chains can often be victims of limitations set by the underlying topology of a state space, leading to correlated samples which can negatively affect the estimator performance. This is the SRRW transition kernel. Consider a Markov chain kernel whose transition probability mappings are this for any vector. And here R is a family of positive functions parameterized by mu sub I, with R sub mu decreasing in x sub I, and the transition probability kernel taking probability distributions as argument are called nonlinear Markov kernels. Stochastic processes utilize nonlinear Markov kernels are called nonlinear Markov chains that can be simulated or generated using self-interacting Markov chains. So this diagram is of SRRW. The green bars indicate the number of previous visits to each node, and the red node arrow indicates tendency of moving toward neighbors visited less often in the past. So for example, if mu is 1 over n, then we can choose a p sub ij like this. because the SRRW kernel can be defined for any given sampling distribution mu. Our SRRW construction begins with R sub mu I taking a polynomial form. So alpha can be perceived as the strength of the self-repellence mechanism designed into the SRRW transition kernel. So for convenience, we formalize the property as a scaling variance. An SRRW kernel possesses Si if for all I and j, these two holds. Computing only requires knowing mu sub k, and Kij is equal to Kij of x. This is the visualization of token algorithm using SRRW versus traditional Markov chain. The SRRW has a smaller tendency to get trapped within subregions of the graph, leading to smaller asymptotic covariance. So their contributions is here, that we show that given any MCMC kernel P, which samples from a target distribution mu, the corresponding SRRW is asymptotically more efficient as a random walk-based samplers. We show that there exists an asymptotic covariance matrix parameterized such as that. And then we have covariance ordering in parameter alpha. We derive an exact form of V in terms of alpha and the spectrum of V. This allows us to show that kernels parameterized by larger alpha are asymptotically more efficient samplers. That is, they achieve a smaller sampling variance. This is done by showing that the asymptotic covariance matrices follow a Loeffner order. In other words, as long as the numerical or computational stability of random walk implementation can be ensured, larger values of alpha are always more favorable in terms of achieving smaller sampling variance. So we study a family of distributed stochastic optimization algorithms. So we replace the standard linear Markovian token by SRRW, which is a nonlinear Markov chain. It means that the draw is from this kernel and then we update it like this. And these beta and gamma here, if you see, are step sizes. Step size sequences decreasing to 0, and k is the kernel. So this update rule in 7 is in fact an example of 2 timescale stochastic approximation with state-dependent Markov noise.